Ms. Petranas back again to continue on with our third segment of our review session. And now we are going to move on into classifying matter into different categories. So the overall classification of matter, actually I'm going to move this, I can't move this down a little bit. Where'd my marker go? I'm going to move this down a little bit. Remember, matter can be classified as either a pure substance or as a mixture of substances. So first we're going to talk about mixtures of substances. So we have two types of mixtures, heterogeneous and homogeneous mixtures. The definition of a heterogeneous mixture is going to be two or more substances combined to make a substance that is not uniform, to overall make a non-uniform mixture. Sorry, I'm skipping some words here. So what we mean by not uniform is that we can see all of the different pieces of our mixture. So some examples of everyday substances would be like Lucky Charms, cereal. You can see the marshmallows, you can see the other pieces, so you can easily separate them. It is not uniform. So ways to separate heterogeneous mixtures are either if we have a mixture of a solid and a liquid, we can separate these mixtures by filtration. Okay, where we have a little filter paper that can catch the solid, and the liquid will pass through into a beaker that would contain it at the bottom. So this would be our filter to separate out the solid. We can also separate with magnets. Magnetism is a physical property. So if you have one substance that's magnetic, we could separate it based on filtration. And some examples of heterogeneous mixtures would be things like sand and water, where the sand would get trapped in the filter paper and the water would go through that filter paper. So even if this water had some salt dissolved in it, it would be able to pass through the filter paper. Because salt and water is a homogeneous mixture, which is a mixture made of two substances, of two or more substances, that make uniform composition. Now, uniform composition means that the mixture would look or appear the same throughout. And all of the particles that are in that mixture are completely combined so that we can't see any of the pieces. Some examples of this would be salt water. And air is also an example because it's a mixture of several different types of molecules. We can't see those different pieces, so it would appear uniform. It means it looks the same. Another example would be an alloy. Now, an alloy is a mixture of metals. When we mix different elemental metals together, they form what we call an alloy. We cannot see those different pieces of metal, so we consider it to be a homogeneous mixture. If you think about the words, the prefix homo means same, and the prefix hetero means different. So we can see in a heterogeneous mixture, you can see all of the different pieces. Different. Okay, it appears different. Where homogeneous appears the same, it looks the same. So ways to separate homogeneous mixtures. So if we had salt water, the way we could separate salt water is by the process of evaporation. Evaporation is when we would boil off the water in an evaporation dish. The water would evaporate, and we could leave the salt behind with heat, so it separates the two substances. Evaporation is used for aqueous solutions, which means substances that are dissolved in water. Now we can also separate homogeneous mixtures of things like air based on boiling points in a process called distillation. Now, distillation separates substances based on their boiling points, where lower boiling points would separate from the mixture first as we heated it up, and then higher boiling points would be separated later. Now, opposite of mixtures of substances, or what mixtures are made of, would be pure substances. Elements and compounds are examples of pure substances. So if I have a container of water and it was only water molecules, that would be considered a pure substance because water is a compound. Elements are all on our periodic table. They are also considered pure substances. So an element is going to be a substance that cannot be broken down physically or chemically. So anything on a periodic table is an element. We can't break them apart. We can't break up their one single atom into anything smaller. A compound is going to be when two or more of these, and I think instead of substances, I'm going to change this, and we're going to say elements that are chemically combined together in a fixed ratio. So what we mean by fixed ratio, for example, is if we have H2O, H2O tells us that the ratio of hydrogen to oxygen is 2:1. That is the only formula that can exist for water, because if we change the ratio of hydrogen to oxygen, then it wouldn't be water anymore. So every compound is defined by the ratio at which the elements are bonded together. So a mixture we just defined, we said there are two or more substances that are physically combined. So compounds are bonded. Chemically combined means bonded together. And then our mixtures, which are physically combined, means that they're just in the same location. They could be attracted to each other with intermolecular forces, but they are not actually bonded together. Since they're not bonded together, they can be separated by physical means. Remember, we just talked about on the last slide, that would be like evaporation, distillation, filtration. If we look at these 4 diagrams at the bottom, our first diagram is each of these particles. There's only one type of particle, and each of them are the same. And it's 2 atoms that are the same that are bonded together. Since these atoms are the same as each other, this is still going to be considered an element, more specifically a diatomic element. Di meaning 2, and so we have these elements made of 2 particles. So this would be our Hofbrinkel. Are all of our elements that exist as pairs. If we look at diagram B, each of these, we have 2 different types of particles here. We have a group of 3, and we have little pairs of diatomic elements. So this is going to be a mixture of, I think this is, the diagram's not great, but I think this is a compound. And then these would all be little diatomic elements. Here in diagram C, there's only one type of particle in here, and this looks like our nice Mickey Mouse particle. So there's only one substance in this box, so this is going to be a pure substance. And that pure substance is a compound of water. Okay, the reason we know that it's a compound is because they're bonded together in a fixed ratio. We have 2 separate types of elements that are bonded. Oh, in this last box, I'm assuming these kind of look like the same thing to me, but we do have 2 different types of particles, so overall we know that this must be a mixture. Moving right along. We have, going into our topic of the atom, if we look at the atomic history, the way the atom was kind of discovered, we start with our first scientist, which is Dalton. Okay, he thought that the atom was a solid sphere. He did not know about subatomic particles. Thomson came along and discovered the electron. He thought that the electrons were just embedded throughout the whole model, so he called this the plum pudding model. So each of these little red dots is representing our electron in the whole model. Now Thomson used the cathode ray tube experiment to discover electrons. And in that experiment, he really just discovered that electrons were negative particles because he observed them being attracted to a more positive plate in this cathode ray tube apparatus. So it's really just he discovered that we have negative particles. Rutherford discovered the nucleus. He used the gold foil experiment, which we see down here at the bottom. And this is really our most important experiment. You really should understand how it works. But he passed these positive alpha particles. He tried to pass them through a piece of gold foil. Most of the particles went straight through the gold foil. This was his observation. So the ones that went straight through, if we think of this layer of gold foil as a layer of atoms, the ones that went straight through, Rutherford said from this observation that the atom is mostly empty space. Some of these particles, however, bounced backwards. So they would, as they were trying to pass through the gold foil, if we zoom in on our atom here, instead of passing straight through, they would hit a nucleus and bounce back and deflect. The ones that bounced back, Rutherford determined that they were hitting the nucleus, and that nucleus was positive. And he knew it was a positive nucleus because the particles that he was shooting through this foil were positive particles. So positives repel positives. So his two observations were that most of the particles passed through. That meant that it was empty space. The ones that bounced back meant that it was hitting a nucleus and there was a positive nucleus in the center of our atom. After Rutherford, we have Bohr, who came up with our planetary model. And the reason we call it the planetary model is because Bohr thought of electrons as orbiting the nucleus on these fixed paths. Okay, so he thought electrons were in orbit around the nucleus. Each of these orbits were energy levels corresponding to the energy of the electron, and these electrons can jump between energy levels. And finally, we have our modern cloud model, quantum cloud model. We also call this the wave mechanical model, which disproved Bohr's model a little bit in that instead of the electrons being on these fixed paths that rotate around the nucleus, we just say that they are in a general region, which we call an orbital or a cloud. So instead of these electrons being on fixed paths, now we know that they're just somewhere in this general region here outside the nucleus. So in terms of atomic history, you should kind of understand the order of things and know the key experiments, the cathode ray experiment and the gold foil experiment, and what their observations led to, such as the cathode ray led to our electron, our gold foil led to the nucleus and mostly empty space. The structure of the atom. In the center, we have our nucleus, which is made of protons and neutrons, okay? And outside, we have the electrons, remember, in that cloud. So if we think about the nucleus a little bit more here, the nucleus, which is made of neutrons and protons, the protons is always going to be the same for every atom of an element, but the neutrons can vary. So for an isotope is going to be an atom of the same element. If they're the same element, that means that they're going to have the same number of protons. The only thing that's going to be different about these isotopes would be that they're going to have different numbers of neutrons. So since they have different numbers of neutrons, they're going to have a different mass. Remember that most of the mass of the atom is in the nucleus. Electrons have relatively zero mass, and protons and neutrons each have a mass of 1 AMU. So an isotope is going to be atoms of same element, different number of neutrons, possibly a different mass. A neutral atom is going to be anything that has the same number of protons and the other charged particle in our atom, electrons. So for an atom to be neutral, we use the term atom, and the protons have to be equal to the electrons. If the protons are not equal to the electrons, we call this an ion. An ion is a charged atom. The way this atom becomes charged is it can either lose or gain electrons. Thinking ahead to the bonding unit, remember that atoms lose or gain electrons in order to have a noble gas configuration. Everything wants to be noble. Everything wants to be like group 18. So, for example, magnesium, when it's neutral, it has a configuration of 282. But if magnesium becomes an ion, it has a 2 plus charge because it's in group 2, which means its configuration just changes to be 2,8. So since it's just 2,8, that happens to be the same as neon because of that full outer shell. So ions are charged atoms that have noble configurations, and they lose or gain electrons to become that charge. A positive ion loses electrons. A negative ion gains electrons. The atomic mass, sorry, there's a lot of information on this slide here, is going to be the weighted average of the masses of the naturally occurring isotopes of an element. I'm going to flip forward. I just want to see if there's an atomic mass problem. Is there? So we can use that information. So thinking about this weighted average of the masses, remember the atomic mass is on your periodic table. So that's the information we can find there. It is not the same as mass number, which is what we're going to talk about in the next slide. Mass number is the mass of one isotope, where the atomic mass is going to be the average of all of the isotopes. Think back to that Candium lab where the mass number was the mass of one piece of candy, where the atomic mass was the average of all of the different types of candy that we had. So if we look at these, the types of problems that go along with isotopes, which symbols represent atoms that are isotopes of each other? Isotope means same protons, different neutrons. If they have different neutrons, that means they're going to have a different mass. So if we look at this problem, we want the same protons. Same protons means the same element. So we can immediately eliminate 4 and 1 because they're different elements of each other. If we look at choice 2, 18 and 16, the numbers at the top are representing our mass number. So they have O16 and O18 have different masses, so these are isotopes of each other. Iodine 131 and iodine 131 are the same mass, so they are not isotopes of each other. Looking at our second question, what is the net charge on a particle that contains 9 protons, 10 neutrons, and 9 electrons? Remember, protons have a positive 1 charge, so if I have 9 of them, that would be plus 9. Neutrons have no charge, so that would be like 0 charge if we're kind of figuring out the net charge, means total. And electrons have a minus 1 charge. There are 9 electrons, so that would be minus 9. So the net charge on this particle would be equal to 0. So this is going to be neutral. It's going to be an atom. And if we looked at what atom it is, we can look at the number of protons, which is 9, which is fluorine. This is a neutral atom of fluorine. Question number 3. The element boron has 2 natural isotopes. Boron 10 has a mass of 10.012 AMU and has a relative abundance of 19.91%. Boron 11 has a mass of 11.009 AMU and has a relative abundance of 80.09%. What is the atomic mass of boron? So this is an atomic mass problem, and we don't have an equation on our reference tables to help us with this. This is just one you have to remember how to do. And it is a weighted average, so what we're going to do is we're going to take that abundance and we're going to change it to a decimal for each isotope. My smartboard doesn't like me. There we go. And we're going to multiply it by the mass of each isotope. So for each isotope, I'll take the abundance, I'm going to change it to a decimal, I'm going to multiply it by the mass, and I'm going to add to it, for the next isotope, the decimal abundance times the mass. So let's actually put this into practice here. If we say, so boron 10 is our first isotope. It has a mass of 10.012 AMU, and it has an abundance of 19.91%. So I want to change that percent to a decimal. So it'd be 0.1991. And I want to take that 0.1991 and multiply it by the mass, which is 10.012. And to that, I'm going to add our next isotope. It says boron 11 has a mass of 11.009 and an abundance of 80.09%. So I'm going to change my abundance to a decimal, which would be, remember, move it 2 places to the left every time. It would be 0.8009. So I'll take that 0.8009, multiply it by the mass, which was 11.009, and I'm going to add those two together to get my total. So when you type this into your calculator, you want to make sure you use parentheses appropriately. So I'm going to make sure I put my parentheses in exactly as I wrote them down. So I have parentheses 0.991 times 10.012. I'm going to close my parentheses, and then I'm going to push plus, and then do another parentheses, 0.8009 times 11.009, close my parentheses, and I got 10.810. Now this makes sense because this number is in between my two masses, and it's a little bit closer to 11, which has a higher abundance. So the one that has a higher abundance, your average should hopefully be a little bit closer to that. I'm going to take a pause here, and you can go on to the next review session. I'm sorry.